Okay, so in chemistry, we're always measuring something. Uh, how heavy something is, how hot something is, how cold something is, uh, how many we have, and we're always just making measurements of everything that we do. But to have a measurements require specific information. Measurements always need to contain some number, and it wouldn't make sense. So if I just wrote five, but 500. If I just wrote 500, well, what does that mean? It's meaningless. It doesn't mean anything because you can't tell what I'm talking about, right? So not only do we have to have, why is this so thin? That a little thicker. Not only do we have to have some number, we also have to have some unit that's going to explain what this is. So I can't just put 500 because that doesn't mean anything. But if I were to put 500 pounds, well, now that means something, right? Whatever it is I measured was probably pretty heavy. If I were to put 500 degrees Fahrenheit, well, now that means something because this is something that's very hot. You know, if I put 500 miles, well, whatever I measured was probably pretty far, right? So here, minus 500 degrees, right? Whatever I measured was probably pretty cold, right? But if I just write 500 minus 500, and I don't have any units here, well, these numbers don't mean anything. I have to have some unit that specifies some physical property about whatever it was that I just measured. Right? So that's what we need here anytime that we're measuring anything. And there are different units. So these are what we consider units. Right? We have an English unit, metric unit, and then what we consider SI units. Right? The English unit's goofy. Right? Pounds, feet, we're used to them, but in science, they're really goofy units. Right? In science, we use metric units, we use SI units, and this is what we use in chemistry. We don't use English units in chemistry. We always have to convert. We'll learn conversions later today. Well, we'll turn pounds into grams or feet into meters, quarts into liters. But English units just don't make a lot of sense because there's no real relationship between English units, right? Um, 12 inches make up a foot. 3 feet make up a yard. 5,280 feet make up a mile, right? That's ridiculous that none of those relate to each other. But I need 100 centimeters for a meter. I need 1,000 meters for a kilometer. And those units are very nice. They're all related by some power of 10. When we go from kilogram, liter, milliliter, right? There's 1,000 milliliters in a liter. There's 1,000 uh, grams in a kilogram. So metric units are very nice. And I want to point something out here is that we talk about volume. The metric unit for volume is liters. And SI units are based off of this metric unit. And we look at it's not based off of liters, it's based off the cubic meter here. So as far as an SI unit goes, We have to think more three-dimensional and think of a cubic meter. So I'm sure you guys have heard of like cc's, right? A cc is a cubic centimeter, right? That's based off of our SI unit, right? So here, this would be 1 meter by 1 meter by, is it by 1 meter? Right. So here, this is where we get our meters cubed, and this represents SI volume. All right. When we take measurements, let me see if I can do this on my tablet here. So when we're taking measurements, when we're taking measurements, let's see, we'll say that this is 0. We're looking at a ruler here. When we take measurements, um, we have what we consider uncertainty. Uh, there's certainty and uncertainty, right? Certainty are values that we absolutely know. We're 100% positive that that value, that number is in the measurement. There's no doubt. Then we have uncertainty. And uncertainty, too thin. Uncertainty is a 1-digit best guess. So in the chat, I need some help from you guys in the chat. So if you had to make this measurement, can somebody give me an estimate? What's your best guess as to what this measurement is? It's just chat. There we go. 3.5. All right, I'll go 3.5. Anybody else? 3.3. Anybody else? 3.4. All right, 3.4. I like that. All right. I was looking for a specific one, but I don't think anybody's got it. All right, so I'm going to give my best guess. I'm going to say this is 3.45. There we go. Oh, and perfect, and thank you very much for that. So Anai says it's 3.45 centimeters. All right. So anytime that you're making a measurement, you are required to have a 1-digit best guess. A 1-digit best guess. So, and it is a best guess. So if we're taking a look at these measurements, that this would be an acceptable measurement. This acceptable. 3.4 is acceptable. But here, I'm not 100% certain that the 4 exists, and I can't be 100% certain that the 5 exists. So this is a 2-digit best guess. So this would not be an acceptable measurement. So anytime you guys are taking measurement, it is just a 1-digit best guess. But I happen to buy this ruler at the 99-cent store, and it's as accurate as it can get. So now I'm going to go to the chemical supply company and tell them that I need some more accurate rulers. And let's change this just a little bit. And let's say I buy a ruler that is now more accurate. And let's revisit these answers. Well, 3.5. Well, here's my 3 point. This is 3.5 right here. There's my 3.5 mark, which means that this is no longer an acceptable answer. 3.3, nope, not an acceptable answer. 3.4, well, 3.4, it looks like I didn't make my best guess. And now Anai has the correct answer. She's got 3.4, and her best guess is this 5. And she has now made a proper measurement. I'm certain that the 3 is there. I'm certain that the 4 is there. And I'm guessing that that's going to be 3.45. So 3.45, 3.47, 3.43, and that we have this measurement here. And now let's go just one more measurement, because this may be a measurement that you may see. And there's nothing wrong with this measurement. If I extend this out just a little bit more, and my measurement is here, well, I'm sure that the 3 exists. I'm sure that the 5 exists. But even though it's on that line, I still need to make my best guess. And my best guess is simply just going to be 0. And that would be my best guess, right? You could also write that as 3.51, 3.49 if you want to try that. But all acceptable answers is that our measurements are done on the accuracy. Our measurements are done on the accuracy here. So let's see here. Valerie, are you just getting here, Valerie? We're 9 minutes 14. We're already in lecture. I've gone over the. Just message me privately or something. You need to be here on time. If you're on a face-to-face class, I would absolutely question you as to why you're being late to my lecture. All right, so those will kind of cover measurements we take there. So some measurements we take are very large values or very small values. Right? So we use a way to write that we consider scientific notation. So scientific notation allows us to write huge numbers or just extremely small numbers. Right? Is that if we write, it wouldn't be very fun to write. Right? That's not an enjoyable number to write here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 25. That it's just a lot easier to write this. So this is just a system we use in order to, again, write really large numbers or really small numbers, right? Really small values. But scientific notation requires a couple of things from you. Now, I don't know what your math instructors, some math instructors who shall remain nameless, tell you that you have to have like point something, point zero zero, point zero. That's not a requirement. In order to have scientific notation, one requirement, the coefficient, this is your coefficient, that is your coefficient, and this coefficient has to be greater than or equal to 1, or, oh, I'm sorry, not or, but and less than 10. And that's the requirement for scientific notation. So if I write the value 0.32 times 10 to the 2, well, is this proper scientific notation? Well, 0.32 is less than 1. So that is not acceptable scientific notation. 32.0. Well, let's take a look. Well, that number is larger than 10, but that's not acceptable scientific notation. Then if I were to write 3.2, well, let's see. 3.2 is larger than or equal to 1. It's also less than 10. Is that this is acceptable scientific notation? And then we can come across this here. 3 times 10 to the 2. Is this scientific notation? Well, let's see. Did I meet the rules here? Here's my coefficient. My coefficient has to be less than or equal to 1 and greater than, I'm sorry, and less than 10. So greater than or equal to 1, less than 10. 3 is greater than or equal to 1. 3 is less than 10. Is that this is scientific notation. There's no such goofy rule that says you have to do this. You don't have to put these additional zeros in if it's not required. There's going to be times where it's required. There's going to be times where it's not required. And if you just simply put the value without the zeros, it is an acceptable form of scientific notation, right? So don't feel pressured to I have to put 0.0. It really is going to depend on the value that you have that you're trying to convert into scientific notation. So how do we convert from scientific notation to decimal form? So this is what we consider decimal form here. So this value here, right? This is decimal notation, 2600.0. This is also decimal notation. Even though I don't have the decimal there, this is still considered decimal notation because I know where the imaginary decimal is supposed to be. It's supposed to be at the end of the zeros, right? So both of these forms here we consider decimal notation. Well, now we need to convert these into what we call scientific notation. So there is a rule, moving the decimal to the left, moving the decimal to the right. So there's two methods here. Use whatever method you want to, right? So the decimal is moved in powers of 10 here. So this coefficient, this coefficient here, right? My exponential power are in powers of 10. 10 to the 1, 10 to the 2, 10 to the 3, and so on. And excuse me, we get those values by the number of times that we move the decimal. So here's my decimal. I'm going to move it 1, 2, 3 times. Because the first thing I need to do is I have to get a coefficient that is greater than or equal to 1 and also less than 10. So how do I convert 2,600 How do I convert 2,600 into a coefficient that's greater than or equal to 1 or less than 10? By moving the decimal place. So by moving the decimal place, if I move it to the left, if I move the decimal to the left, my power is going to be positive. So we moved it 3 times. There's my decimal here. And that's where I get my coefficient. Now, however many times that I've moved that decimal place. I know there's an imaginary decimal here. It doesn't have to actually show. And I'm going to move it 1, 2, 3, 4, 5 times. I moved it 5 times to the left. So I have a coefficient of 5. If I move this decimal to the right, I need to make this value here into a value that's greater than or equal to 1, less than 10. And by adjusting this decimal 1, 2, 3, 4 places, well, now I'm going to have a negative exponent. So if we move it to the right, our exponent is going to be negative. If we move it to the left, my exponent is going to be positive. This rule only applies if you're going from decimal notation to scientific notation. It does not apply to both because there's a different set of rules going from scientific notation to there's a different set of rules going um, from scientific notation to decimal. I'm sorry, I got sidetracked here. So I'm sorry about that. Different set of rules going from scientific notation to decimal notation. We can't use the same rules. Is that here? If we see a positive exponent, because we see a positive exponent, we cannot use the same rule and move the decimal to the left. It doesn't make sense. Because it's positive, here's what happens. 2.6000. If I'm going from scientific notation to decimal notation, I cannot move this decimal point to the left. It's now the opposite. I have to move this decimal to the right. Negative exponent, I have to move this decimal place to the left. Right? So we do have opposite rules there. I honestly don't even like this method. So what I do is this is the number I use. Anytime that I'm going to do this, I just think of the number 1. I'm going to use the number 1 to determine whether my exponent is positive, whether my exponent is negative. And all I need to know is just this number 1. Is the value I'm trying to convert larger than or less than 1? Is it larger? Is it less than 1? If it's larger than 1, if this value is larger than 1, my exponent will always be positive. I don't have to think right, left, right, left. If my value is smaller than 1, my value is going to be negative for this exponent. So it doesn't really matter left, right, right, left. Right? If I give you a value, 9,909. Okay, 9,909. Is this value larger than 1 or is it less than 1? Well, this value is definitely larger than 1, which means that my exponent is going to be positive. I'm going to adjust my decimal so that I get a coefficient that's greater than or equal to 1. And I know my exponent's positive because this value is larger than 1. Well, if it's less than 1, well, is this number greater than 1 or less than 1? It's less than 1. I know my exponent is going to be negative because it's a small number. I'm going to adjust my decimal, 6.21. That's a value between 1 and 10. And I know my exponent is going to be negative. And I can do the same thing down here. I can use the same rule here, going from scientific notation to decimal notation. Doesn't matter what the value is here. Let's see. 1.23 times 10 to the 6. Well, if my exponent is positive, that means that when I convert this, this number has to be bigger than 1. Because this is positive, this value has to be larger than 1. Well, the only way I can make it larger than 1 is if I move that decimal to the right. And now I have a value that's larger than 1. We can do the same thing here. Nope. Well, it's a negative exponent. And if it's a negative exponent, I know that that value is going to be less than 1. Less than 1. There's no way I'm going to move this decimal place to the right. I have to move it to the left. And now I have a value that's less than 1. Right? So this is how we deal with those exponents here. All right. So here, express this number into scientific notation. Well, is this value less than 1 or larger than 1? Well, it's less than 1, which means that my exponent is going to be negative. I'm going to take this decimal and I'm going to move it so that I get a coefficient that's between 1 and 10. My new coefficient is now between 1 and 10. I move that decimal 3 times, and because it's a value less than 1, my exponent is negative. This should be 10 to the 4. Convert it from scientific notation into decimal form. Well, this 4 is positive, which means that my answer is going to be larger than 1. Well, if I need a number larger than 1, 1, 2, 3, 4, and I now have a number that is larger than 1. All of these values here, you need to know all these values. You have to memorize all these values here. You need to know that tera is 10 to the 12, gig is 10 to the 9, meg is 10 to the 6, kilo is 10 to the 3. There is some confusion, though, using this specific table. But you do have to know the prefixes and their values. So when we talk about these prefixes, these values here are for your metric units. Once you guys have your textbooks, this will be in your textbook, right? So there's no, if you, real quick, if you guys are, let's see here. For the very first lecture here, if there we go. Actually, you know what? I'm going to give you guys a website here, BBC Chemistry. If you just type in BBC Chemistry, this shows up here. And for those of you that don't have your books yet, the labs are not on here. There are no labs here, but there are lecture notes here. So look familiar, right? I've already used that. There's here's the table. This is your actual text. It's just on a PDF file online. Do you have to buy the book still? Yes, you still need to buy the book because at the end of this textbook are the labs. You can't do the labs without the textbook, right? Except for the first two, because I'm probably going to give those to you. But other than that, these lecture videos are not mine. So if you go to this page, these lectures are of Professor Kennedy, right? You're more than welcome to watch them. I won't stop you. He won't stop you. But those are not my lecture videos. But again, if you want to follow along to the lecture, and I lecture by this here. So that's always available to you guys. All right, so let's get back here. So you do have to no. So for question, segregation 3 or 3.0. Well, it depends. I'm going to answer that, Hugo, but I'm not going to answer it right now. But I will answer it shortly because it really depends on the value that you're trying to convert. Because not both of them would be correct. Only one, but again, it depends on the value, on the measurement. Okay, but I will answer that question in just a few minutes when we get to that section. So here, in order to use this, I put where it says value, I put metric units up here, right? So I put metric units here, and I'll show you how to use this a little bit better because it's a little vague on how this works. So let's see. We'll put centimeter. We'll use a centimeter. Centimeter, or centi, right, is 10 to the minus 2. How we use this list here is for your metric units of grams, liters, meters. So if I wanted to know how many meters, if I wanted to know how many meters are in a centimeter, this is how I would write it. I would say that 1 centimeter is equal to 10 to the minus 2 meters, and not the other way around. So there is confusion here, and some students will look at it this way. They go, oh, well, kilometer is 10 to the 3. So they say, okay, there's 10 to the 3 kilometers in 1 meter. Well, let's see if that makes sense. A meter is a little less than a yard, which means it's a little less than 3 feet, right? So if you know what 3 feet is, right, about the size of a, maybe your desktop, that's that probably close to a meter. 10 to the 3 means 10 times 10 times 10, which is equal to 1,000. A kilometer is about, I don't know, 3/4 of a mile. So this 1,000 kilometers, and a kilometer is about 3/4 of a mile, is definitely not equal to 1 meter. So again, values here, the value that we use here are for grams, liters, and meters. And how I would correctly write this is I would say 1 kilometer is equal to, well, the prefix for kilo is 10 to the 3, 10 to the 3 meters. That if I want to know how many milligrams are in 1 gram, well, no, I should reword that. If I want to know how many grams are in 1 milligram, well, here's 1 milligram. And I know milli is 10 to the minus 3, and milli, this 10 to the 3 represents the number of grams. 10 to the minus 3 grams. If I wanted to know a microliter, 1 microliter, 1 microliter. Well, here's my liters, and I know that micro is 10 to the minus 6, so 1 microliter is 10 to the minus 6 liters. And this is how we use this table, right? So you do have to know all of these values, though. So this is one of the tables that you're going to want to memorize for the exam. Now, this will probably help answer Hugo's question here. So Hugo asked if we're supposed to put scientific notation to 3 or 3.00, which would be correct, or would both of them be correct? Well, only one of those would actually be correct. So if we're looking at measurements, right? Some values in our measurements are what we're going to consider significant, and some are what we're going to consider as insignificant. Right? So anytime we have a non-zero number, any non-zero number is always significant. What do I mean by non-zero number? Easy. It's any number that's just not zero, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are all our non-zero values, right? So anytime we have that, we're just going to count each value up, and that's going to give us the total number of significant figures. We might call it sig figs or significant digits. It's all the same. So if I write the value 1,356, well, I don't have any zeros here, so I'm going to count 1, 2, 3, 4, and there are 4 significant figures in this number. How many significant figures here? 1, 2, 3. There's 3 significant figures. So non-zero numbers are always easy. It's the zeros that kind of give you a little trouble, right? Zeros are sometimes significant. So times when they are significant is when we consider leading zeros. I'm sorry, insignificant. Leading zeros are always insignificant. We never, ever count the leading zeros. And these are the zeros that are in front of our non-zero numbers. Here's my non-zero numbers, and the zeros in front, we never have to count them. Here's my non-zero numbers. Anything in front, I never have to count them. There's no exception. There's no special rule. They're just always insignificant. We don't ever count them. Doesn't matter how many zeros that I have. Any leading zero is never ever significant. All right. And then we have zeros that are significant. And this is what we consider what we call captive zeros. They're the zeros that are sitting between two that are sitting between two non-zero numbers. So here, captive zero. Because they're in between two non-zero numbers, I have to include them. So here's 1, 2, 3, 4, four significant figures. Captive zero. Leading zeros. These are leading zeros, and I do not have to include leading zeros ever. Ever. And I only have to include my captive zero. So we go 1, 2, 3, three significant figures. Captive zeros right here. Because they're in between two non-zero numbers, I have to include them. 1, 2, 3, 4, 5, 6, 6 significant figures. Right? Right? I don't ever have to include leading zeros, but these are captive zeros, and I do have to include them. 1, 2, 3, 4, 5, 5 significant figures. All right, so we know when we don't have to include them. We know when we do have to include them. And now comes the time to where we sometimes include them. Trailing zeros, these are the zeros that are at the end of numbers, right? So here is a trailing zero. Here is a trailing zero. Here is a trailing zero. Here are trailing zeros. So I've come up with a formula that's going to allow you to figure out when and when not to use, or when and when not to count those trailing zeros, right? Uh, but I've used this formula. I've used this formula for the last several years, and it's always worked. I haven't found a case where my formula doesn't work. It's worked in every single case. I don't have any papers written on it. I didn't publish it, but I think I might publish it. We'll see what happens. But I'll give you the formula that I use to determine whether trailing zeros are insignificant or not insignificant. So the formula is simply this. There it is. That is the formula. But make sure you take notes on this because this is priceless here. So we have to make sure we remember this formula. All you need to look at is just this decimal place and ask yourself, right? Do you physically see the decimal? So if I have a number, here I have two numbers. In this instance, do I physically see the decimal? No. I know that there's an imaginary decimal. I'm not asking you, is there an imaginary decimal? No. What I'm asking you is, do you physically see it? If you don't physically see the decimal, you do not have to include the trailing zeros. One significant figure. If you do see the decimal, then you have to include the trailing zeros. And that's all you need to do for trailing zeros. Do you see the decimal? Do you not see the decimal? Do you physically see the decimal here? No. I know that it's at the end of the zero, but I don't physically see it, so I only have to count these values here, and I have 2 significant figures. Do I see the decimal place? Yep, I sure do. It's right here. I have to include this trailing 0. 1, 2, 3, 4, 4 significant figures. So all just depends if you physically see this decimal. Let's write this value here. Well, there's a lot of zeros here. Let's see which ones we have to include, which ones we don't have to include. Well, do we have to include leading zeros? I know there's a decimal here, but this is only for trailing zeros. That's it. Has nothing to do with leading zeros. So decimal point or no decimal point, we never have to include leading zeros. Do I have to include this 0? Well, yeah, because it's a captive 0. If I see the decimal place, then I have to include these trailing zeros. 1, 2, 3, 4, 5, 5 significant figures. All right, well, let's see. I have a value here. Leading zeros, don't ever have to count them. Captive 0, yep, I have to include that. If I don't see a decimal point anywhere, I don't have to include these trailing zeros, which means that I only need to include 1, 2, 3, 4, 5 significant figures. So again, this is only for trailing zeros. Leading zeros never matter. Captive zeros always matter. Trailing zeros depends if you physically see that decimal point or don't see that decimal point. Right? So how many significant figures does each value have? Let's look at A. Do I include the leading zero? Oh, I have zeros there. These leading zeros, I don't have to count them. We just have 2. B, I see the decimal point. I have to include both of them, 3 significant figures. I don't see the decimal point anywhere. I don't have to include those zeros, 2 significant figures. In a coefficient, we're not worried about this at all. In a coefficient, we're only worried about these values. In scientific notation, we're only worried about the coefficient, that we're not worried about the 10 to the minus 5. Just the coefficient. Captive 0, 3 significant figures. Do I see the decimal point? 1 significant figure. I see the decimal point, 4 significant figures. Captive 0, I have to include them. 3, 4, 5, 6, 7 significant figures. I see the decimal point, I have to include them. 4 significant figures. I see the decimal point, I have to include it. 5 significant figures. So now going back to Hugo's question here. 3 or 3.00. Well, I'll tell you which one is right. So here, if I wrote this, using Hugo's question here, so if I have 300 and 3 100 point. Well, in scientific notation, I'm going to have 2 different answers here. When you convert from scientific notation or decimal notation to scientific notation to decimal notation, you want to keep the significant figures the same. In this top value here, because there's no decimal point here, I don't have to include these zeros, and I'm simply just going to write 3 times 10 to the 2. I see this decimal point here. This is going to be 3.00 times 10 to the 2. 3 significant figures, 3 significant figures. 1 significant figure, 1 significant figure. Does that answer your question, Hugo? All right. So now we'll cover a different type of number. So all we've been talking about are just measurements. Um, excuse me. Measurements that we take, and that is definitely one type of number. The other type of number we have are what we consider exact numbers. Exact numbers don't have any uncertainty, right? There's no uncertainty, excuse me, in an exact number. And exact numbers are what we find when we count things or in what we consider as what we call definitions, right? So these are what we consider definitions, right? So 25 students, I can count all of them, right? If I look at the participants here, I have 39 students and I counted them all. I don't have about. I don't have 39.5, 39.1. I have 40 students here in the chat, and I counted all of them. That's an exact number. If I had on my desk, I have 3 markers. I counted them. I have 2 cups. I counted them. Right. Uh, those are what we consider exact numbers, and exact numbers don't have any uncertainty. When we're considering exact numbers, because they don't have any uncertainty, remember this here. Do not forget it. Exact numbers, we do not use them to determine significant figures. We do not use exact numbers to determine significant figures. I'm going to repeat that one more time, and then I'm going to ask you a question. Exact numbers are not used to determine significant figures. So, in the chat, can somebody tell me how many significant figures are here? And remember what I just told you. We don't use exact. Ah, Raquel, you're a genius. There are 0 significant figures here because we don't use exact numbers to determine significant figures. And that's going to be a really important concept when we're doing calculations, because sometimes we have to calculate and use exact numbers, but we can't let that sway us in determining the number of significant figures. So there are 0 significant figures here. We don't use them to determine the number of significant figures, exact numbers. Significant figures, 0, none. We don't use them. All right. So we do have rules for rounding. Now the rules for rounding don't change. We don't come into chemistry and we don't change these mathematic rules. I'm sure all of you know how to round a number. But in chemistry, we definitely ask you a different way. We don't change the rules, but we ask it a lot differently. So if I asked you, and you can answer in the chat, that's fine. If I asked you to round this number here, Can somebody round that number for me? 20. Perfect. You round it to 20. If I ask you to round this number, can you round that for me? 50. Perfect. So that's how we round. Those rules don't change. Anything 5, 6, 7, 8, 9, we round it up. 1, 2, 3, 4, we round it down, and those values stay the same, right? But again, we ask it a lot differently. So here, if the one I'm going to underline right here, how many significant figures are in this value here? 2. How many significant figures are in this value? 1. There's 2 digits, but only one of those values is significant. I have 2 digits, but we go from we go from 2 significant figures down to 1 significant figure. Hold on to that concept. So if I were to ask you, oh, let me make that. I want to make this too complicated here. 7,800 and if I asked you to convert this number, what we look for is I want you to convert this. I'm sorry, not convert. I want you to round this to 3 significant figures. And this is how we ask you in symmetry. Well, so we have 782. Now, I'm not giving you a hard time, Antoinette, right? I'm not giving. I just kind of want everybody to understand what's going on here. So we said 782, and that is 3 significant figures. But if we're rounding 7,821, would it be correct if we round that to 782? That would mean that if do we 21 and we round it to 2. So let's carry, we don't do that. We go from 21 to 20, 2 sig figs to 1 sig fig. So what do you think we can do to adjust 782 so that we round it to 3 sig? Yeah, perfect. Yes, 7,820. 4 sig figs to 3 sig figs, and I still have something in the thousands, right? So how about we take the same value, 7,821, and let's round this to 2 significant figures. 7,800. What if I asked you to round it to 1 significant figure? 8,000. So it's not that we changed the rules, but we definitely ask it a different way, right? That we can't just, if I have 4 digits, when I round it, I still have to have 4 digits, right? So we don't want to just get rid of any, but we do have to add, we do have to add a significant 0. So we change it from 1 to a significant 0. We change 21 to significant 0. We change 821 to significant 0. And then there's going to be times where we actually have to add insignificant zeros, right? So this is what we're doing. We do right now, we just added insignificant zeros. I should underline the significant. We just added insignificant zeros, right? And there is going to be a time when we do need to add significant zeros. Okay, so multiplication, if you're following along in the text or on the PDF that's online, I do multiplication and division first, and then I go back and I do addition and subtraction, because multiplication and division are just easier to learn right off the bat. When we're talking, because sometimes we have to take these values, these measurements, and we have to multiply them together, but we still have to maintain the right number of significant figures. So our rule for multiplication and division is that we look at all of our values and we find the value, the measurement, with the fewest number of significant figures. And our answer has to reflect the fewest number of significant figures. Doesn't matter what the calculator says. The smallest number of significant figures, and our answer has to reflect the same. So if I look at my measurement here, and I look at this measurement here, I know there's no units here, but let's just pretend there's units. 2 significant figures, 3 significant figures, my answer has to be 2 significant figures. This is what the calculator tells you. Calculator tells you 9.198. But if we're going to satisfy the rules for significant figures, we find the measurement with the smallest number, and our answer has to reflect that. 4 significant figures, 1 significant figure. My answer has to maintain that, and our answer is 1 significant figure. Doesn't matter what the calculator says, we have to round that to 1 significant figure. 2 sig figs, 4 sig figs. My answer has to be 2 significant figures. Your calculator, if you were to put this problem into your calculator gives you this answer of 2. Now, everybody here, pay attention. Your calculators are stupid. Don't depend. Your calculator will let you down constantly. Constantly lets you down. You can't trust your calculator 100%. It will lie to you. Calculators do not give you significant figures. If this is the answer your calculator gives you, you are required to determine the significant figures. Always. Your calculator will not do it for you. Don't be lazy and assume that what the calculator tells you is the correct answer. Because if you see this on something like this on the exam, and you go, oh, well, hey, my calculator says 2. My calculator says 2, so I'm going to circle that answer, and then they move on to the next question. They go, oh, yeah, look at, I got 2.5 points in the bank. No, you don't, because you circled the wrong answer. The answer is 2.0. 4.3. Maybe let me double check the calculation. Let's see. 4.311 divided by 0.07, and I get 60. Okay, just want to make sure that was correct. So as far as let's backtrack a little bit. Darlene had a question here. All right. So if I look at these values, Darlene, you tell me in chat how many significant figures are in this value, Darlene? 4. Perfect. That's not a fraction. I'm just writing. Let me write 4 significant figures. It's not a fraction. I'm putting 4 there so I know how many significant figures. How many significant figures are in this number? And remember, you have leading zeros. 1, right? We don't have to. So it's a 1 significant figure, which means that my answer, regardless of, this is what the calculator comes out to. Your calculator tells you 61.58. But my answer, because this is the lowest number of significant figures, my answer also has to reflect 1 significant figure. This has 4, this has 2, and because I don't see the decimal point over here, I don't have to count that 0, and I have one significant figure. I know that it's 60, and I count the 60, but as far as significant figures go, I don't have to include that 0 in my significant figures, and I have one significant figure there. Does that help, Darlene? Okay, perfect. All right. Oh, let's go over the last one here. It doesn't matter because this is all multiplication division. We're always looking for the lowest number of significant figures. So here, I have 3 significant figures, 2 significant figures, 3 significant figures, 2 significant figures. 2 happens to be the lowest. My answer has to reflect 2 significant figures. Right? So it doesn't matter how much multiplication division you have, how complex it is. If it's only multiplication division, just look at the measurement with the smallest number of significant figures, and your answer has to reflect that same number. Now come times for, this is for addition and subtraction here. So as far as addition and subtraction goes, we don't look at the number of significant figures. So um, ignore everything that I taught you for multiplication division because you cannot use the same rules. It's different rules for addition and subtraction. What we use is we use the number of decimal places. And our answer has to reflect the smallest number of decimal places. 1 past the decimal. 2 past the decimal. My answer has to be 1 past the decimal. I know that there's 3 here, and I know that there's 3 here, and I know that there's 3 here, and that's a happy coincidence. But we don't go by the number of significant figures. So if we look at some values here, let's go with let's go ahead and add these together here. And here, again, don't look at the number of significant figures. Let's first write out our answer and or a calculation first. So I have 114.10. Here in the top value, I have 2 past the decimal. 1 past the decimal. So my answer can only be 1 past the decimal. Then my answer is 114.1. Doesn't matter that one is 5 significant figures, one is 3 significant figures, and don't assume that your answer is just simply 114 because it matches the smallest number of significant figures. Those rules are for multiplication and division. We're doing addition subtraction. The rules change. We go by the smallest number of the smallest number of decimal places. The smallest number of decimal places. Let's change this up a little bit. 1.2. And we're going to add this up again. So we got 114.29. Well, nope, that didn't work out. Let me erase one of these values here. Oh, let's put that in there. All right, there we go. So here, we need to make sure that we round correctly, right? Is that we're two past the decimal here, we're two past the decimal here, we're one past the decimal here. Our answer can only go one past the decimal. But before we get rid of this 9 here, this 9 affects that too. And our answer would be 114.3. So make sure that we are rounding correctly when we're asked. Let's see, how about if I add these together? Well, let's go ahead and add them up. 122.7629. I have 0 past the decimal. I have 4 past the decimal. Well, it looks like 0 past the decimal wins. Then my answer cannot go beyond that decimal there. That my answer is 123. And you may also be asked to convert these values into scientific notation, right? Your lab is going to have something similar to this, right? So let's go back up here and let's convert this to scientific notation. And if I convert this to scientific notation, I need a coefficient that's between 1 and 10, right? So we got 1.143 times 10 to the 2. Right. So I've now converted that into scientific notation, right? So you'll be asked to do something like that in the lab. But definitely a different set of rules here than we see in multiplication and division. Sometimes we have to do mixed order of operations, right? Sometimes we have multiplication, division, and addition, subtraction. So here we see an example of that, right? So we have 250 divided by 125 plus 0.1, and we have to maintain the right number of significant figures. So here, what I would do is, well, we can't do the addition until we solve this, right? So let's stick with the rules for, let's do this, and we're going to use the rules of multiplication and division. The rules for multiplication and division say the smallest number of significant figures. 2 sig figs, because I don't have to include this, and 3 sig figs. My answer has to be 2 significant figures. When you take this and you put it into the calculator, the answer is simply just 2. But again, your calculator is going to constantly lie to you, and you have to determine your own number of significant figures. I need 2 significant figures, and my answer is 2.0 plus 0.1. Well, now that I've used the rules for division and multiplication, now I can apply the rules for addition. My answer here is 1 past the decimal, 1 past the decimal. My answer has to be 1 past the decimal. Right? Don't just assume. Don't take a look at this whole thing and go, oh, let's see, 2 sig figs, 3 sig figs, 1 sig fig. My answer only needs to be 2. No, that's completely wrong. We use the rules for multiplication division. Then we use our rules for addition subtraction, and we get this answer of 2.1. One that's more complex here. I'm going to do what's in parentheses here first, and this is addition subtraction. 1 past the decimal, none past the decimal. 6745 plus 4.7 is 6749.7. So let me do that here. So we have 6745 plus 4.7 equals, well, I have to go 0 past the decimal, which means that this value is going to be 6750. None past the decimal. All right, so now that I've done that, well, now I can finish the top portion and go 3 significant figures, 4 significant figures. Well, let's see what that is. 6750 times 3.76. And my top value is 25,380. But I can only have 3 significant figures. I have to round this to 3 significant figures. 25400. And I've rounded it to 3 significant figures. Well, now let's do this bottom portion here. 2 past the decimal, 1 past the decimal, 2.7, and I'm 1 past the decimal. That's the rules for addition and subtraction. So now we can do this. We go 2.7, and now we can go ahead and put this calculation in. 25400 divided by 2.7. I have to go with 2 significant figures, regardless what the calculator says. 2 significant figures says that this is my answer. But my calculator said this, 9407.407, repeating. But I have to round it to 2 significant figures, right? So we keep these rules in place, apply multiplication division when you have it, apply addition and subtraction when you have it throughout your calculation. So because of the English unit that everybody uses, we're always faced with converting quantities from English units. Converting pounds to grams or converting feet to meters, Fahrenheit to Celsius. So we use a method we call dimensional analysis. And what we're going to use to do that is we're going to use conversion factors. Conversion factors come from definitions, right? I've already kind of introduced definitions already, right? So here's an example of a definition. 1 foot equals 12 inches. 100 centimeters equals 1 meter. These are definitions. These are exact numbers, right? These are definitions. We're going to take our definitions and convert them into what we call a conversion factor. So here, let's convert this into a conversion factor. Conversion factor is a fancy chemistry term for fraction. That's all it is. Let's turn this into a fraction. Well, here's one way to do it. I can put 1 foot over 12 inches, or I can write it as 12 inches over 1 foot. I can do 100 centimeters over 1 meter, or I can write it as 1 meter over 100 centimeters. Okay, so conversion factors come from these definitions, and all a conversion factor is simply just a fraction made from that definition. In the front of your guys' textbook, you'll see this page here. It gives you a bunch of definitions that can all be used to turn into a conversion factor, right? If I'm looking at this, I can write 1 pound over 454 or I can write it as 454 grams over 1 pound. Right? So here, right, examples of definitions. So even D here, but I wanted to take a look at D. D is also a definition. The accepted toxic dose of mercury is 0.30 milligrams per day. Milligrams per day. Well, that's kind of like miles per hour, right? That per is where we're going to put this uh, fraction at, right? So 0.30 milligrams per day, right? So even this is considered a definition, and we can get conversion factors. Don't forget, or we can write it as 1 day, get 0.30 milligrams. Uh, let's see. Let's write another statement here. How about stainless steel is 12% by mass chromium. So there's my definition. So here we just have to do a little bit of analytical thinking here on how to turn this into some conversion factor, some kind of fraction. Well, I could start with this. How do I turn 12% into a fraction? Well, that's simply just 12 over 100. That's 12%. By mass. Well, what's a unit of mass that we've talked about today? How about grams? Grams is a unit of mass. So I got 12 grams over 100 grams, but it's 12% mass chromium. And the rest of it would be stainless steel. Right? So even this statement here, and then we can write it as maybe 100 grams of stainless steel over 12 grams of chromium. So those are definitely, excuse me, definitely different ways we can write this. Let's see, I'm not ready to move on to this just yet. We do have to do some conversion problems. So let me get to a blank page here. All right. So I'm actually going to do one from your textbook. So let's look at a homework problem. Oh, let's see, what can we do? Um, we'll go from nanometers to angstrom. So let's do 1.4. So 1.4 in your textbook, as far as the homework goes, let's see, we have 683 nanometers, and we need to convert that to something we call angstroms. Well, we're going to use definitions and conversion factors in order to do this. So nanometers, if you memorize, so let me go back to a slide here. So if we use this table here, and we know nano is 10 to the minus 9, we can say that 1 nanometer is equal to 10 to the minus 9 meters. Well, write this down because we're going to use that. And we also need a second conversion factor. So our second conversion factor, oh, sorry for that. Our second conversion factor comes from this table. Get dizzy, I'm sorry. All right. Is we're also going to use this. 1 angstrom is equal to 10 to the minus 10 meters. An angstrom is equal to 10 to the minus 10 meters. Where's my blank page? There it is. So 1 angstrom is equal to 10 to the minus 10 meters. And we know that 1 nanometer is equal to 10 to the minus 9 meters. So we need conversion factors. So you are going to be required to do this a lot. So let's convert these definitions into conversion factors. I'm going to put 1 angstrom over 10 to the minus 10 meters. Or it's 10 to the minus 10 meters over 1 angstrom. I'm going to do the same thing down here. I'm going to put 1 nanometer over 10 to the minus 9 meters, or I'm going to put 10 to the minus 9 meters over 1 nanometer. And I want to convert 683 nanometers. So if you're not familiar with cross-canceling, we need to set up a fraction or a conversion factor so that we can cancel out these nanometers. So this requires that the nanometers be placed in the denominator. Even though both of these conversion factors are from the same definition, only one of them is going to allow you to cross-cancel. Is that if I set this fraction up, 10 to the minus 9 meters over 1 nanometer, is that this in the numerator cancels this out in the denominator. Well, we're going to need a second conversion factor. Some of your conversion factors will only require one conversion. Some might require 2, some might require 3. So here, only one of these is going to cancel out the meters that we see in the numerator. That means that my meters have to be in the denominator to cancel that out. Even though they both come from the same definition, only this one will work. These units in the numerator cancel out these units in the denominator. And now that we've canceled those, well, now we can go ahead and calculate that answer. So we're going to have 683 times 10 to the minus 9 divided by 10 to the minus 10. 6,830. For those of you, if you're having trouble with your calculators and scientific notation, after the lecture today, I'll stop the recording after the lecture. You can use your video feed, and I can help you use your calculators so that you're using scientific notation correctly. So now let's take a look at significant figures. Remember what I said earlier about these are exact numbers because they're definitions. And exact numbers don't use any significant figures, just our measurements. So no significant figures, no significant figures is that we have to have 3 significant figures, 1, 2, 3, there's no decimal, that this is the correct answer. Let's see, let's do another one here. Get kind of messy, need to find a blank page. This is kind of blank. Let's see. Let's see, what if I wrote how many seconds in one day? If we want to know how many seconds are in a day, well, let's start with 1 day. Let's see, how many seconds are in 1 day? You know what? No, I don't like that question. Let's do something else. How many? Oh, that's going to give me the wrong. Let's see what your textbook has. No, they don't give you much to work with here. Miles to hours to meters per second. Let's do. Won't do that specific one. How about we go from meters per second to miles? That's about that. Let's do that. So if I have and for those of you that see this, like in your textbooks, you might see this. I don't ever use this slash mark. Is that please try not to use this. Your calculations are going to come out awkward. Is that convert this into a proper fraction that you can see the units, miles over hours, right? Don't use that little slash mark there. All right, so let's convert this into miles per hour. All right, so let's convert that to miles per hour. So first we're going to start with 3,206,002 meters per second. We want to see that in miles per hour. Let's work on getting rid of the meters first. Excuse me. Sorry about that. If we go to our units, we're looking for something that's going to convert miles. So we have miles here. And I don't see anything else with miles. So 1.61 kilometers. And then we can probably convert that to meters. So we're going to use both of those definitions here. 1 mile equals 1.61 kilometers. One mile equals 1.61 kilometers. So I'm going to get two conversions factors from this. I'm going to get 1 mile over 1.61 kilometers, or 1.61 kilometers per mile. And then we had another definition of 1,000 meters is equal to 1 kilometer, or 1 kilometer is equal to 1,000 meters. Well, if we're going to convert meters first, well, I need that in the denominator. So here's the conversion factor that I'm going to use. So we're going to put 1 kilometer over 1,000 meters. So we don't need this one anymore. And we need to get to miles. This is our target mile. So now we're going to use one of these. I have to get rid of kilometers, so I need kilometers in the denominator, which means that we're not going to be using this one here. So we're going to multiply this by 1 mile over 1.61 kilometers. And now we have to go from seconds to hours. So in order to get rid of these seconds here, well, what's the definition from seconds to hours? Well, how about we do this? How about we go from seconds to minutes and then minutes to hours? So there's 60 seconds in 1 minute, and then there's 60 minutes in 1 hour. According to my definition here, in order to get rid of this in the denominator, I need seconds in the numerator. 60 seconds for every minute. And let me cancel these units out. So this cancels out this. These meters cancel out these meters. These seconds cancel out these seconds. But I still need to cancel out minutes. According to our definition here, there's 60 minutes in 1 hour. These units cancel out, and I'm only left with 2 units now. We had to convert from miles to hour, and the only units that I have not canceled out are miles and hours. So let's make this calculation real quick. 326,002 divided by 1,000 divided by 1.61 times 60 times 60. Let's see, conversion factor, 0 sig figs. 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 1, 2, 3, 4, 5, 6 significant figures. Then our answer here, 7, 2, 8, 9, 4, 8.5. So let's round and we'll make that a 9. Miles per hour. So that's pretty fast, right? So again, some of these are going to get very complicated, but you have to be able to do this cross-canceling, right? Cross-canceling, so practice, practice, practice. We're going to do one more of your homework problems. You'll have more practice in the lab. The lab also has conversions that you guys need to do. So, but I do want to get over and help you with one of these homework problems here. So homework problem number 1.5. So homework problem 1.5, and I'm going to read it. A physician has ordered 37.5 milligrams of some drug over 15 minutes. And I'm going to take that, that's kind of like saying per 15 minutes, right? So I'm going to put that over 15 minutes. If the drug is available in 2.5 milligrams per milliliter, how many milliliters are you going to need to give every 15 seconds? Well, let's go ahead and figure this out. When I look at this question, if the question is asking you, how many milliliters, this unit needs to be in the numerator. Has to be in the numerator. If I'm asking how many milliliters, I don't want to know how many per milliliters. I want to know how many milliliters. And if I look at this, right, we're chemists. We get to do cool stuff here. I know that this is in the denominator, but we learned about conversion factors. We're allowed to flip these back and forth however we feel like. So this is not the only way that I can write this. I can write this as 1 milliliter over 2.5 milligrams. And by doing that, look at this. Milligrams in the numerator, milligrams in the denominator, and I can potentially cancel something out when I set this up. So if I put 1 milliliter over 2.5 milligrams, and I multiply that by 37.5 milligrams every 15 minutes, well, we can go ahead and cancel out these units. But I still have 2 units here. The 2 units I have are milliliters and minutes. So we have to get rid of those minutes. But luckily I have some information here. As awkward as this seems, force yourself to do this. I know it's awkward, but this is a measurement, data, it's information. Multiply this by 15 seconds. Go, Alex, that doesn't cancel out. What are you doing? You're messing everything up. No, trust me, it'll work. If this looks funny to you, just do this. For those of us that have OCD, boom. Oh, all right, Alex, that looks much better. Thank you. All right, so just put it over 1. You don't have to look up a definition for seconds to minutes. I'm not asking you to put in how many seconds are in 15 minutes. No. All we need to do is get rid of the units. You know that there's 60 seconds in 1 minute. Cancel this out. I have to put 60 seconds over 1 minute. And by doing so, these units cancel out. And I'm only left with 1 unit now. I'm only left with these milliliters. So I got 1 times 37.5 times 15, divide by 2.5, divide by 15, divide by 60. Let's see, 2 significant figures, 2 significant figures, 2 significant figures, 2 significant figures. My definition is, I don't use those, so my answer is 0.25 milliliters. Don't be tempted to do this because there are students that will calculate this answer and they'll just put the answer over 15 seconds, but that's not what we're asking for. We want to just know the milliliters. We're not asking how many mils per second. We're strictly asking you how many milliliters. What's the milliliters? The milliliters is 0.25. All right, so now we're going to move on to our topic of density. So density is this ratio. Density is a ratio of mass, the mass of some substance, over the volume that that substance occupies. Right? So note here, right, that this is volume in the metric system, and this is volume based off of our SI units. Right? So they're interchangeable. So as far as mass over volume, so density is equal to mass over volume. The mass in grams over volume in milliliters. The mass in grams over the volumes of cubic centimeters. You'll need to know that for the lab, tomorrow's lab as well. So tomorrow's lab is going to involve calculations regarding density. So if we're given a problem here, what's the density? Well, we just need our formula of density. Density equals mass divided by volume. So if we set this up, our mass, and I know it's mass because it's in grams, and grams is a unit of mass, 48 grams. And as far as the volume, the volume isn't explicitly given here. So I'm going to make a very crude drawing of a graduated cylinder is that we put water in this. There's tick marks on the side of it, with some values. This will be 30, this will be 25 or something, I don't know. But what happens if this is my water level, if I put this piece of metal into this graduated cylinder, as soon as I do that, this water level goes up and I'm going to have a new water level. So the difference between these two values here, the difference between that is my volume of whatever I put in there. And that's what you have here. So if I put this piece of metal in a graduated cylinder and that level goes from 25 milliliters to 33 milliliters, the difference between those is my volume. The final volume minus my initial volume. Here, we're going to be doing division and we're going to be doing addition subtraction. So let's take care of addition subtraction first. 33 minus 25, 0 past the decimal, 0 past the decimal. My answer is 0 past the decimal. It's not 2 sig figs because this is addition subtraction. The smallest number of significant figures, that's for multiplication division. So here, I'm going to put 48 grams over 8 milliliters. Now I'm going to use the rules for multiplication division. 2 sig figs, 1 sig fig. My answer has to be 1 significant figure. Right? Sometimes we're not that lucky though. This one was pretty simple. But sometimes we're not given either. Maybe we need to look at one where we're not given the volume or we're not given the mass. And that's going to be something like this. So here, the density is given to us. Density equals mass over volume. We're asked to calculate the mass, so we don't know what this value is, which means that we need to rearrange this formula. So in order to figure out what the mass is, well, our mass is going to be density times volume, and this is going to be equal to mass, right? If you don't know how to do this, all I simply do is what I do on one side of the equal sign, I have to do the other side, right? So if I times this by volume, I also have to times this by volume. These units cancel out, and I have my mass is equal to volume times density. Right? If we're given let's see, if we're given, density equals mass over volume. If we need to figure this out, well, that means I'm going to need that in the numerator. If I want to know the volume, the volume 20 minutes. If I have to isolate the volume, well, this is how we would do it. We would multiply this by volume, multiply this by volume, and these units cancel out. And I get volume times density equals mass. But I want the volume by itself, which means if I have to divide this by D, I also have to divide this by D. These units cancel out, and I get volume equals mass over density. So there's 3 different formulas here. Density equals mass over volume. Mass equals density times volume. Volume equals mass divided by the density. So in order to calculate mass, we're going to be using this formula here. Mass is equal to the density times the volume. Our density is 1.05. I'm not going to use the slash mark. I'm going to put it into a proper looking fraction. times the volume, 3, and again, if it looks funny, just do this. Just put it over 1. Then we can calculate this out. Get 1.05 times 377.0. Let's see. 3 significant figures, 4 significant figures. My answer is going to be 3 significant figures, 396 grams, because these milliliter units will cancel out. So you may be asked to do that at some point. Here we have some temperature scales. So Fahrenheit's the English system. Right? Then we have Celsius and Kelvin, our metric and SI units here. So the Fahrenheit is kind of odd here. There's a 180-degree difference between when water boils and freezes, right? Water freezes at 212, freezes at 32 and it boils at 212. And it's unlike Celsius and Kelvin. There's a 100-degree Celsius degrees difference, 100 Kelvin difference between when water boils and freezes. That's because Fahrenheit wasn't developed around pure water. That Celsius was developed around pure water. So pure water, when it boils, they gave it a value of 100 degrees Celsius. When it froze, they said, okay, that's going to be 0 degrees Celsius. Fahrenheit was developed around seawater, around brine, right? So they have a different value there. So seawater, freezes at a different temperature than pure water freezes. Right? So again, that's why we see this awkward difference here, this 180-degree difference here. One thing in common that Fahrenheit and Celsius have, though, is that they can go in the negative. Right? I can go negative 10 degrees Fahrenheit, negative 20 degrees Celsius. But Kelvin, we cannot. Kelvin stops at 0 Kelvin. There's no negative in the Kelvin system, right? There is no negative. So we do need to learn how to convert from Fahrenheit to Celsius, Celsius to Kelvin, Kelvin to Fahrenheit. So here are these units here, or here are these formulas here. So am I going to want to write these down and keep these handy? And we'll actually do we're just going to do one calculation here. So let's do about 20, about 74 degrees Fahrenheit. So 74 degrees Fahrenheit, and let's convert that into Kelvin. So in order to convert that into Kelvin, we need to convert Fahrenheit into Celsius first. So we're going to go Fahrenheit to Celsius, and then from Celsius, we'll go into Kelvin. So in order to figure out Celsius to Fahrenheit, Fahrenheit to Celsius, this is what we want, I'm sorry. In order to figure out Celsius, we're going to take our degrees Fahrenheit, which is 74 degrees Fahrenheit. Subtract it from 32, and that gets divided by 1.8. So 74 minus 32 is subtraction. 0 past the decimal, 0 past the decimal, that we get 42 divided by 1.8. And this comes out to, let's see, two significant figures, 23 degrees Celsius. Well, now if we want to figure out Kelvin, well, now what we know what Celsius is, well, we go Kelvin is equal to 23 degrees Celsius plus 273. This is equal to 296. 0 past the decimal, 0 past the decimal. My answer is 0 past the decimal. So I don't spend too much time on calculating these temperatures. You have the formulas available to you. Just plug in the numbers and out spits the answer. So I think we're winding down here. We're almost done with this. So heat. We talk about heat and temperature. That those are two very different concepts, right? That heat heat is a total sum of energy. Temperature is just an average. So what I mean by that is that if you're just at home, the temperature, I don't know, here it's 75 degrees, right? So 75 degrees in my office, and that's the average temperature here. That's taking into account my temperature, because I'm definitely not 75 degrees, but it takes into account my temperature, my computer's temperature, my monitor's temperature, the ceiling fan spin around, whatever's in my office here. It's averaging all of the heat here, and we come out with some average temperature. If I wanted to increase the heat, I'd have all my dogs come in. I got 8 dogs. I'd have them all come into my office, right? And the average temperature, the heat would go up because I'd have more heat in here. If I want to decrease the temperature, I'd turn everything off, monitors. I'd leave the room, and the temperature would slightly drop because there would be less energy here. So temperature is an average of all of the energy that happens. Heat's different. Heat is a total sum of energy. Units that we use for heat, we're going to use 4 different units for heat here. So here we have what we call the cal, the kcal, this cal with a capital C. You learn that chemists are pretty lazy, and we need shortcuts for everything, right? As far as this goes here, right? K is kilo, and kilo is 10 to the 3, which is 1,000. So 1,000 calories takes 1 kcal. But I think chemists got a little bit lazy, and they didn't like writing the K, so they turned the C into a capital, so that 1 kcal is equal to 1 cal, right? Like, how lazy can we be, right? We need shortcuts for everything we do, right? My wife agrees. Okay, so those are going to be units of heat. Now, we have 3 units here that represent heat, not temperature, but heat. So there's one more, and that's what we call the joule here, right? So that's the 4th one. So as far as calories are concerned, this is a unit of heat that raises the temperature of 1 gram of water by simply 1 degree Celsius. Okay, and that's what we consider a calorie, right? It raises the temperature of 1 gram of water by 1 degree Celsius. So the more calories that are required, the more heat to raise the temperature of that gram of water by 1 degree Celsius. And then we have joule, it's J-O-L-E, and it is pronounced joule. And 1 calorie is equal to 4.184 joules. So again, we have 4 different units for heat. Now, when we talk about something we call specific heat in calories per gram degree Celsius, let me use the small c here, calorie over grams degree Celsius, or joules over gram degree Celsius. Right. So we talk about specific heat. This is the heat needed to raise the temperature of 1 gram of a substance, not just water, right? But the temperature needed to raise 1 gram of substance of any matter that exists by 1 degree Celsius. And this is what we're going to call specific heat. So every substance any material around has its own specific heat, right? Its own specific heat. So here is, you don't have to memorize this list. These are just kind of examples, right? So we see the specific heat here between ice and between gold. That it takes a lot more heat to melt ice than it does to melt gold. It takes more heat to melt ice than. I'm not talking about temperature again. I'm not talking about temperature. I'm talking about heat, right? Here, right? Metals heat up pretty quickly, right? And we're not talking about melting it, but we're talking about raising the temperature of it by the material by 1 degree Celsius, right? If I have 1 gram of gold, it takes this much heat. Good morning. That's my granddaughter coming in. It takes that much heat to. Sorry about that. All right, I'm back to the lecture now. Okay, so it takes that much heat to raise 1 gram of gold than 1 gram of ice by 1 degree Celsius. 1 gram of mercury compared to 1 gram of water, 1 degree, right? So heat again, metals tend to heat up a lot more quicker than water does. So we have this formula for heat. So heat, and this Q here, the Q is not a unit. We know the units. So Q, the units for Q are going to be joules, calories, kcalories, or calories. Like those are the units for Q. Q is just kind of variable in here that represents what the heat is going to be, right? So we take mass times the specific heat and multiply by some change in temperature. So you'll see this in tomorrow's lab, and it'll be in the video that you guys watch for tomorrow's lab. Lab number 2. But if we're going to make some calculations here, so here we're going to calculate the specific heat of some metal. So here's our formula. Q is equal to mass times specific heat times the change in temperature. So this delta equals change. So when I write delta T, this means, right? Delta T is final temperature minus initial temperature, right? So delta T is equal to T final minus T initial. All right, so here we have some information. So do we know what Q is? Yep, we sure do. Q is in joules. That's one of my units for Q. So I know that Q is equal to 87.6 joules. To raise the temperature of 51.0 grams, I know that that's my mass. And change the temperature by 3.9 degrees Celsius. So my delta T is 3.9 degrees Celsius. So what we don't know is we don't know what the specific heat is. So that's what we're going to calculate. We have to rearrange this problem. And if we rearrange this problem to isolate specific heat, it's going to be Q divided by mass divided by the change in temperature, and this is going to equal our specific heat. So now we just have to throw these values in here. So I got 87.6 joules divided by mass, which is 51.0 grams, divided by 3.9 degrees Celsius. And I know I wrote times there, but I said divided by. Lecture's almost over. If if you guys have to go, you have to go. Lecture's almost over. So here, 87.6 But again, the way I read this is 87.6 divided by 51.0 grams divided by 3.9 degrees Celsius. So even though it says times, there's two ways to calculate this out. So this is one way to calculate it out. Whichever way you want to calculate it, be my guest. So one way to calculate it would be the 87.6 joules, and then I'm going to multiply 51.0 times 3.9, and I get 198.9 grams degrees Celsius. And then I'm going to do, again, so I got 87.6 divided by 198.9, and I come out, let's see, 3 sig figs. I'm looking at the original information here. I'm looking here. 3 sig figs, 3 sig figs, 2 sig figs. It's all multiplication division. My answer is going to be 0.44 joules per gram degree Celsius. Oh, yep, joules per gram degree Celsius. So this would be my final answer. That's one way to calculate it. It's not the only way to calculate it. If I write it up here, I'm going to rewrite the problem, 87.6 joules over 51.0 times 3.9. $87.6 divided by 51.0. Anything in the denominator, this is what I work with. Well, if you're doing it, Darlene, if you're doing it the first way I talked to, so here, if we're looking at this one down here, then yes, you would multiply this first, and then you would divide it, and that's definitely one way to do it. But I don't like doing those calculations. Personally, I don't do that. But it is one way to do it, and I won't stop you, but you'll get the same exact answer. The way that I do it, I remember the rule, if it's in the denominator, I divide it. So if I'm looking at this problem here, and I'm going to enter this in my calculator, I'm going to go 87.6 divide by 51.0 divide by 3.9. Because it's in the denominator, I pretty much just ignore this, and because it's in the denominator, I just hit divide by 3.9. So I do this in one calculation. I go 87.6 divided by 51 divided by 3.9, and I come out with the exact same answer of 0.44. However you guys want to do it, I'll leave it up to you. Right? Doesn't really matter to me. That covers the lecture here. That covers the lecture, so let me go ahead and stop this.